Okay, so in this question, we're asked to consider a binary phase diagram of two compounds A and B that react to form a compound AB, and then we're given the phase diagram. And the phase diagram is here, and then we're given some questions to answer. So the first question says, identify a point or a feature of the diagram where that indicates to us that incongruent melting occurs. So basically, what indicates incongruent melting is usually this kind of T shape that we see here. So this T shape here indicates incongruent melting, or you can say the intersection of the liquidus curves indicates incongruent melting. So the point zeta there, or the point eta indicates incongruent melting, however you want to state it. So around about, what's that, 0.62-ish there, the intersection of the liquidus curves, or the point eta at 0.67 will indicate incongruent melting, because of course the compound AB2, which forms here, AB2, which is there, that line compound there, decomposes before it reaches the liquidus curves, which is indicative of incongruent melting. And why do I know it's at 0.62? Well, because of the composition of AB2. So if we have mole fraction of B, it means that 2/3 would roughly be 0.67. So if B is 2/3 of the compound AB2, so 2/3 of the mole fraction would be 0.67. So in other words, it'd be roughly about 0.67 mole fraction is where the compound would exist. Right. So that's how you would go about identifying an incongruent melting compound in a phase diagram. So now you know the compound is melting incongruently. Of course, if it were melting congruently, we would see somewhere we would see a peak somewhere, and we would have seen that kind of feature. All right. What is the composition of the eutectic mixture, and at what temperature does it melt? Well, the composition is here at epsilon, so it's that. So it's roughly, what would we say there? So that's 0.3 there. So that's what 0.26. So xb equals to 0.26, and the temperature, let's say that's about T approximately 195 degrees Celsius. So for epsilon, those are the conditions. So that's the B part. Okay. So that's what I would say for the eutectic mixture where it melts, and that's its compositions. Of course, that's XB, and I mean XA is implied, but you can also say XA would of course then be 0.74. Just to be more explicit. Right, so then question C asks us, label all the region of the diagram according to the chemical species that exist in that region and their phases. Indicate the number of species and phases present at the points, or the number labeled by the Greek letters. Okay, so let's first just label the regions, and then we can look at the speech, the Greek letters, because the labeling will help us with the Greek letters. So of course we always start here at the top, so because we know that's the pure liquid region, and because it's incongruently melting, we know we will only have liquid A and B on top here. We won't have the compound AB2 at the top here, which will only be pure A and B on top here at the liquid, and it will be pure liquid above the liquidus curve. Okay, then we will move to this region over here. We will have predominantly A, so in other words, there should be some A crystallized here. So A solid should be here. There should also be some A in the liquid form. Well, in principle, so then you know, so it's A in the solid form plus some liquid. But we can specify, because we know it's incongruent melting, that we should expect there should be some A in the liquid form plus some B also in the liquid form that composes our liquid. And then opposite of that eutectic, then we would expect the first time, because it's opposite of the line, so in other words, opposite of where the incongruent compound or the line compound forms. So that's the first time we should expect to see our compound to form, but of course it will only appear in the solid state, so it will be there, but we also expect to see some of A and B in the liquid form, because it will be, generally speaking, it will be AB this plus liquid, but the liquid composes of A liquid plus B liquid. Right. Then here at the bottom should all be solid. So this is a solid region. But what is the solid region? Well, we're in the region where it's predominantly A, so we expect to have A as a solid, but also AB as a solid. Right, AB2 as a solid. Because we're that side of the phase diagram where A is in excess, so in other words, all the B is reacting with A to form AB2, and then there's still some A left to crystallize below the eutectic. So below the eutectic, there will be a solid region, and then that reaction will occur to form AB2, and some A is left over. Okay, let's move to the other solid region. So this is also a solid region, of course. And then we're now the region where there's predominantly B, so in other words, B is in excess now, so all the B that does not react will be left over, but the B that does react will form, of course, AB2 solid, right? And it makes sense that they shifted to this way because there needs to be a lot of B in excess for it to form AB2, because we need more B than we need A for it to be in excess, because there's a 2-to-1 ratio of AB and to form AB2. Okay. And then just the final region, of course, B is in excess, so which one will be the solid? So B will be the solid. It's above the melting point of AB2, so we don't expect any AB2 to be here. So we just expect some B to be in the liquid form, and then also a little bit of A to be in the liquid form. Okay. So that's basically the labeling of the diagram. Right. So now we need to look at these Greek letters. So they asked us to number or to give the number of components. So in other words, say how many distinct chemical species there are, and then say how many phases are present at these points. So that's best explained by just doing as an example. So let's look at beta. So I'm going to do it as like a comma separated list. So the number of components here, so we see so beta is on a line. So in other words, we must look at both sides of the line. So in other words, what is on both sides of the liquidus curve? So we see we have A as a liquid, B as a liquid on both sides, and A as a solid. So in other words, there are three chemically distinct species, if we count A as a liquid and A as a solid as two chemically distinct species, which we probably can. I mean, you would be able to distinguish the liquid from the solid, because you would be seeing, liquid A maybe floating, or solid A sinking in liquid A. Or if you think about water and ice, you would see the ice floating on top of the water, for example. So you'll be able to distinguish between the solid and the liquid species. So then we would say we have three chemically distinct species. And how many phases do we have here? Well, it's kind of easy because we have a liquid and a solid here. So we have two species. So we have some sort of liquid, and the liquids are the same. It's Al and A liquid and B liquid, and then we just have the one solid. So don't really have to think too much about it. Okay, let's look next at delta. So I just want to move these two just a little bit. That's the one I want. There we go. So delta. Okay, so what do we have? We have two chemically distinct species. Do you agree? So we have A as a solid and AB2 as a solid. there should be some difference between them, maybe a color difference, or at least they should separate, or something. There should be something different between them. They shouldn't be exactly the same. They will have different crystal structures or whatever. But me saying they have different crystal structures, even though they're both solids, should also remind you of the fact that they will be different phases. So we actually have two phases in this region as well. Because remember, phases aren't necessarily just solid, liquid, and gas. Phases can be, solids can have different phases. So if you think about the sulfur phase diagram that we looked at way at the beginning of the course, or of this theme, we had monoclinic, rhombic, phase transitions, so different crystalline structures for the same solid state. So that means we have different solid state phases, and AB2 and A are two different solid phases of in this same solid state. So that means we have two phases and two chemically distinct species. So we label it as 2,2. Okay. So let's move to epsilon. Epsilon, of course, so how many chemically distinct species can we count? So epsilon, we have to look at this region, this region, this region, and this region, because it links to all four of them. So we have, maybe we should write a list of what epsilon entails. So epsilon entails A liquid, it entails B liquid, right? Plus there's some A solid that comes in. So I'm moving sort of this way around. We're looking at that. So A liquid, B liquid, then A solid comes in. Then we've already had A solid, so then AB solid, AB2 solid comes in. AB2 solid comes in. And then we've already had AB2, A liquid and B liquid, so we don't have to write them again. So we have four species, four chemically distinct species here. Okay. And then how many phases do we have? Well, we have the A solid state phase, we have the AB2 solid state phase, we have the A, and then we have the AB liquid phase. Right. So because the liquid phase we can't distinguish, that's just a liquid. There's not two different liquids, they are a miscible liquid that we say. So in other words, they mix in all proportions, we assume. Otherwise, they wouldn't be able to react. That's a very important point, actually. I should have probably said that earlier. So if they weren't able to react, they wouldn't be able to make the phase diagram. So they're miscible. So that means we have three phases at this point. Okay. So let's move to the zeta point. So zeta, so let's just do that again. So zeta connects to how many points? To three phases again, or to three, so if we're looking at it like that, so we have A liquid, B liquid, A, B2 solid, A liquid, B liquid, we've already had, so that's, so we're counting components, so in other words, it has one A liquid, B liquid is a component, A, B2 solid is a component, then we have A liquid, B liquid already counted, and then A liquid, B liquid is already counted, and B solid. So again, we have four components. How many distinct, or how many phases do we have at zeta? Well, we must count again. So we have the A liquid, B liquid, so that's a phase. We have AB2 solid, that's a phase. And then we have A liquid, B liquid, that's the same phase as before. We have A liquid, B liquid, that's the same phase as before, but we also have B solid. That's a different solid state phase to AB2 solid. So we have three solid state phases, or two solid state phases, and one liquid phase, one miscible liquid phase. Okay, so again we have a 4-3, same as the eutectic point. Of course, you can calculate the degrees of freedom for these. That might be an extension to this question, to calculate the degrees of freedom. So let's quickly just do that for vibes, So F is equal to, what's it, C minus P plus 2. So number of components, so components will now be your chemically distinct species or whatever. So that would be, well, actually your component is 2. So you have 2 minus your number of phases is 3 plus 2. So in other words, you have the degrees of freedom of, no, that's not the components. It should be, it's right, it is right. So you have one degree of freedom, and that makes sense. You can move on the line, is how you can move. Anyway, cool. So now you have that. Then, what's the last one? We can do theta. Yeah, theta. So again, we're in a solid region. So we have 2 chemically distinct species. You agree? So yeah, we have B solid and we have AB solid, AB2 solid. And of course, they're 2 different phases because AB2 solid is a phase and B solid is also a phase on its own. Okay. Right. So I think that takes care of that question. Now, the next question asks, we need to sketch cooling curves for the compositions. So all the lines, all the dotted lines, plus the one there at eta, we need to sketch. So I'm going to draw like a little graph, and that was D. I think it was D. Let's try and draw them all on the same. Yeah. Okay, so now let's look at, so what I'm going to consider is, so we're considering something that cools down at this composition and what happens to it. So if it's cooling down at this composition, we're going to see it cools down, and at this temperature here, we're going to see a rate change, right? It's going to start cooling down. There's a rate change because we have some solid crystallizing. So we go from a liquid to some solid plus liquid, so a rate change. And then at the eutectic again, so again here at this point, we see some solid plus liquid turning into completely to solid. So we should see leveling off of the curve and then slowly cooling down again. So in other words, we should see something like that, then a rate change to some point at the eutectic, and then some cooling off. So in other words, this is at the point epsilon, and this is at the point, what was it again? Was this beta? You can also use like a line or something just to indicate that that is indeed like a rate changing point, like a point where the rate changes. You can do whatever you want, really. I mean, you can even just point and say rate change. If you want. And this is, of course, temperature versus time. Okay. And you don't have to be too specific. You can indicate where this happens. I mean, it's probably about 350 degrees Celsius, so that's 350. And the eutectic that we say was 195, so 195. Okay, and then you want to draw all of the eutectics at the same temperature. So I'm going to try and do that, but I know it's kind of difficult to do by hand. So I probably might ask you only 1 or 2 if I ever do, not like 17, but this is just so you get an idea of all the different ones. Right, so the next one that we're asked is here at the epsilon, so that's at the eutectic. So if we look at a cooling that happens at the eutectic, just like that. What happens? So it will cool down. It's just going to cool down until it reaches the eutectic temperature, and then it will transition from liquid to solid, and then it will cool down again. There's no difference there. So in other words, it just reaches the eutectic point, plateaus, and cools down. Simple transition from liquid to solid, no difference. And it's actually a congruent melting point, that, but yeah, anyway. Right. Then zeta. So zeta is a bit, well, it's not too interesting, but so it's another another kink point. So we take a point, so we expect it's going to have a rate change there. It's going to have a plateau there, and then just normally cool down again as such. So in other words, at some point zeta is going to start cooling down all the way to the eutectic, cool down, plateau, my apologies. So at the eutectic, it plateaus, and at some point, I have to draw a zeta. Yeah, it's not the worst zeta in the world, but anyway, it's not the best one as well. Yeah, so that at some point zeta, and that zeta is technically it's lower than beta, but so it's difficult to draw these things completely to scale. So I will understand if you don't draw them completely to scale. I won't crucify you. Yeah. So it's the basic point that says you understand once it crosses the liquidus curve, it's going to have a rate change because we go from pure liquid to liquid plus solid because we have a phase change. So there's another phase introduced, and then again when we go from the solid plus liquid region to the pure solid region, we have another change in the rate. Okay, and then we're looking at the next one we look at is here on the line compound actually. This is where something interesting happens. So we have a few transitions here. We're going to have the one on the liquidus curve. Then we have the one where we have the AB2 forming. And then we should see another one here at the eutectic. So we actually should see two rate, what do we call it? Two rate slows or two rate changes. So in other words, we see a rate change and we see another rate change all the way to the eutectic, which then cools and then plateaus and then stops. So this is at the eutectic, this is at eta, it's a terrible eta, and this is at some other point, that other point that I call, we can call it nu. Let's call that nu so that we just have a name for it. So that's at point nu. So that's the first time we have a rate change. Then we go at eta where AB2 starts forming, and then at epsilon where it plateaus. So that's something that you should be aware of, because of course there at the eta point we have the formation of AB2 for the first time. So at what did I call it? At nu we only have B solid and B liquid and A liquid, and then at eta we have another phase being introduced, and then at epsilon we have the complete solidification of the system. Okay, and then finally we have this system, or this process here. So this one is a very nice straightforward one again. We're going to cross the liquidus curve into the solid plus liquid phase, and then we just go into the solid phase. So again, going to have a rate decrease at kink somewhere until our epsilon, so the eutectic point, and then we had our point where we crossed over. So yeah, that's kind of what we expect to see in our cooling curves. We don't expect anything else. So now you've seen how you would probably see where the line compound forms, or where you will see where the composition is. So if once you've made that composition of the correct compositions, in other words, you mixed something in the ratio that forms AB2. So in other words, a third A plus 2/3 B. You've mixed something of that composition, then you will see that cooling curve, and then it will correspond to that point on the phase diagram. So that's, if you draw more complex things, then you should be able to see that nicely. All right. So let's move to question E. Consider the following questions regarding solubility. What is the solubility of B in A? So I'm just going to rub out my little lines here. Let me move this. Ooh. Come on. Okay, move that there. So the first question asks, what is the solubility of B and A at 500 degrees Celsius? So at 500 degrees Celsius, let's draw a line here. We see that we're in the liquid region. So A and B should be completely soluble. So they said A in B, right? Yeah, or B and A. So B is 100% soluble in A at, that's a very terribly drawn at 500 degrees Celsius. All right. Because in all proportions, because it's both liquids, so I mean, and they're miscible. So in other words, there should be no issue with the two being soluble in one another. So that's basically what the question is trying to assess, whether you know that. I think I answered it earlier a bit more in breadth, so I'm not going to go back into detail on that. So the second question asks, what is the solubility of AB2 in A at 370 degrees Celsius? So 370, I would judge that to be around about, where would I say is that? Around about there. So give or take something there. So it corresponds to a composition of, so let's just call this point x1 for the moment. It has a composition of roughly x1 equals 0.66. So it's going to give us that B, we have solid B in this region, but there is no AB really. So I mean, we have solid B, so we have solid B. So it'll be in equilibrium with some liquid, which is of course B liquid plus A liquid, right? That's what we see in the graph. We wrote that earlier at this composition, x equals at x1 equals 0.66. So that's where we are. We are here in this region over here. This is I mean, I know x1 is technically to the left there, but I mean we're in that region is where we're talking about. But that's above the melting point. So the melting point of AB2 is that. So that's above the melting point of AB2. So which is above, oops. The melting point of AB2. Hence, you can either see it as all the AB2 is dissolved in A, or no AB2 is dissolved, is soluble in A. Because there is no AB2 to be dissolved in A. I mean, there's no solid AB2 to dissolve in A or dissociate into A, or you can give the counter argument in the sense that all the AB2 has dissolved into A. So it's 100% soluble. It's a difficult question to really answer into that sense. So that's why I would rather say there's AB2 is not soluble or it does not exist. AB2, because it does not exist, which is above the 10 centimeters because it does not exist. Right. So because it doesn't exist at that temperature, there's no use giving any discussion on it. Right. So that's just basically to test whether or not you understand where AB2 actually exists or not. Okay, the next question is an interesting one in the sense of it asks now what is the solubility of AB2 in B at 300 degrees Celsius? So let's draw another line, 300 degrees Celsius. So 300 degrees Celsius cuts our phase diagram about there. So let's call this X2 at 0.46. Okay. So 0.46, so let me just write that down for us here. So X2 equals 0.46 is what we have. This is, of course, the composition of B. So what we're looking at here is we're looking at basically, so we're looking at the region of AB2 solid plus B liquid plus A liquid. So and they're asking just to look at the dissociation basically, because AB2 solid isn't dissolved in the liquid. It's a solid. It is there present. But the question is essentially asking how much AB2 solid is present in the liquids. So we can think of it as AB2 solids dissociation into A plus B plus B, so its components in the A liquid plus B liquid. So that's sort of the image that you have to have in your mind. So basically just, it's not a solubility in a sense, it's actually more asking how much AB2 solid is present at this point. It's basically what it is, but it's asking for the solubility, but because that's just how to express it in terms of the phase diagram. Right. So we're looking for a way, so in other words, so I'm asking how much AB2 solid is present. So in other words, at this point in terms of B, so, or how much is present. So we're looking for something, so like the number of moles expressed as a fraction of something. So for example, the number of moles expressed as a fraction of the number of moles of A. So we'll get to that notation what I used just now. So the number of moles of AB2 divided by the number of moles of A will give us the solubility, right? So let's call it the solubility. So if we say that ratio of, if we get, for example, 0.5, then we know there is half of the components in this region at this composition is AB2 compared to the composition of A, well, the number of moles of A, right? So then we know that that's the ratio that we're looking at, for example. So that's something that we could calculate from the information that we're given. Okay, so let's use the notation C and NA. So remember, we used at some stage if we state things like C is equal to AB2, for example. So if we use this, then what is the number of moles of A equal to? Well, the number of moles is equal to, of A is equal to number of moles of the A in the liquid. So in other words, Na, so let's call that just Na. And plus the number of moles of A from the compound. So because there's of course A coming from this dissociated compound, right? And then there will also be to calculate xb, which is in this case equal to x2, we're going to need the moles of B as well, right? Because that is equal to Na plus Nb. So what is the number of moles of B? Well, the number of moles of B is equal to twice that of AB. So that's twice that of Nc, because for every 1 mole of AB2, there's 2 Bs that will come from the dissociation. Okay. So let's plug that in. So that becomes 2Nc over Na plus Nc plus 2Nc. That gives us 2Nc over Na plus 3Nc. Okay, and let's just quickly rearrange that. So then we have x2Na plus 3x2Nc is equal to 2Nc. In other words, x2Na is equal to Nc times 2 minus 3x2. And then we can say Nc over Na is equal to x2 over 2 minus 3x2. What is x2? It's that 0.46 that we said there at the top. So 3 times 0.46. Plug that into our calculator. Gives us 0.74. Okay. So that tells us that for every 1 mole of Na, so in other words, every 1 mole of A, there is 0.74 mole of AB2 that is dissolved in B. Right, which makes sense. I mean, makes sense in the sense that, so that's just how to explain it. So in other words, for every 1 mole of A that dissolves in B, there's 0.74 moles of AB2 that dissolves in B, which is essentially what we've gotten. So I hope you followed this argument. So I always need to draw it back to the calculation of the mole fraction. You just need to find a way to express whatever you're calculating in terms of the mole fraction. So that's quite easy with the AB2. If we just had AB, for example, then you would have had NC and NC. If you had AB3, then you would have NC and 3NC, or whatever. And then you just need to go through the calculation. All right. So that is essentially it for this question. It's a very long question, I would say quite difficult, but I tried to cover a bunch of concepts in one. So that's why it was quite long and tedious. But yeah, I think it's quite valuable. So, especially this last one, probably a bit more intense than it should be, probably more than it should be, but now you've learned something. All right.
I just thought I might go back to a point I made earlier, which might have not come across as direct as I wanted it to. So earlier I calculated the number of degrees of freedom here at the point zeta, and I said F is equal to C minus P plus 2. We said the number of components is 2, it's A and B, and then P, the number of distinct phases, is 3, and then plus 2, and then we got, there's 1. But what does this 1 degree of freedom actually refer to? This 1 degree of freedom refers to the only parameter that's not on this phase diagram, and that is the pressure. The only thing that can vary here, the degree of freedom that can vary here, is the pressure. We can vary the pressure of the system, so not the mole fraction and the temperature. That's a degree of freedom that can be varied. Technically, if you want to look at the diagram itself, you must calculate f prime, remember, and then you calculate c minus p plus 1. Then you lose a degree of freedom. So if you're looking at the two-dimensional diagram, and then, I mean, you're going to get just, then you get f prime is 0 at the point zeta and also at epsilon. So at zeta, no, that should be the other way around. The point zeta and at epsilon, you get it. You have a 0 degrees of freedom, because if you move in any direction at those points, there's sort of like triple points on these diagrams. You agree? There's like different lines that connect there. If you move in any direction at those points, you will disturb the equilibrium. So you cannot change any of the variables that are plotted on this diagram without disturbing the equilibrium. So that their variance or their degrees of freedom need to be 0 for this diagram. But looking at beta, for example, you expect to see 1 degree of freedom, for example, because you should be able to move. In a similar fashion, you should see for the other points at least 1 degree of freedom, because you should be able to move at least in one direction. If not 2 directions. In other words, because you should be able to move in at least 1 or 2 without disturbing the equilibrium. Right, so that is essentially it. You might be asking, so let's quickly just look at something, because some of you might calculate it and wonder, but you might not get that far. Some of you might not care. If you look at, for example, at the point theta, you might say components, so the number of components is 2. And then you're going to say, well, C minus P, so number of phases 2 plus 1. And then you're going to get, well, your degrees of freedom is just 1. Why is your number of degrees of freedom here just 1? And not 2, because you're in an area. So why can't you change the pressure or the temperature and the number of, or the mole fraction for the point theta, because you should remain in this area. It shouldn't, the number of phases and whatever is not really going to change. And the reason is because this ratio of AB2 to B is complicates things to a relative to a relative amount, also it's to a certain extent. That's the wording I'm looking for. So in other words, it's not as clear cut as what it was previously, that we looking at an area. We now, with having AB2 incorporated to the system. So yeah. Anyway, because we're not looking just at pure A and pure B, so we can't just move in an area without disturbing the equilibrium. So you just have 1 degree of freedom. You can, for example, move the temperature, or you can disturb the composition. But you can't do sort of both of them at the same time and expect the system to still have the same equilibrium. Just because you have B is going to react with A, and that's going to also affect the system. So you can change one variable at a time, because there's sort of a implied variance with the reaction taking place as well. Okay, if that makes sense. I hope that makes sense. So there is already a degree of freedom in the sense that there's a reaction also taking place with this. You'll see the same for if you calculate delta. There's also only 1 degree of freedom. Yeah, but if you of course had a pure AB system, then you would see you have 2 degrees of freedom. So, yeah, that is essentially that's just the point I wanted to clarify. So you just need to make the distinction whether or not you're calculating F or F prime. That's the important point. And of course, if you're calculating F, then you just need to check what you're plotting. If you're plotting then T, then of course, if you're calculating F, then the degree of freedom is actually the pressure, the one that's not plotted. So if you're plotting T versus mole fraction, then the other variable is the pressure. If you're plotting pressure versus mole fraction, then the other variable is, of course, the temperature. Yeah, and that kind of thing. So I hope this clarified something. Maybe something you didn't even pick up, but yeah. Okay.